So we are going to be looking at APDL. APDL, mechanical APDL. I cannot remember what it stands for. This has been used massively throughout many different applications. I've seen it used all over the place. One of the big selling points from Ansys' perspective about APDL is the solvers and its efficiency. And mark my words, as an efficient tool, it is crazy good. It does away with all the sexy rendering, does away with all the sophisticated imagery, and it just goes down to the core of what simulation is about. So what I'm going to do is open up Horizon. And again, I've never tried to run APDL through Horizon. We'll give it a go. If it does fail, don't worry. It was a bit of an experiment anyway. But this is the best way I could describe it is it does look very primitive, but it is so scalable. Now do keep in mind, this as a software tool, this is dimensionless. Now what I mean by that is you must make sure that you operate in the dimensions that you're thinking about using. If you're operating in millimeters, everything must be held in millimeters. You can't go, right, that's 10 millimeters and then that's, I don't know, 500 centimeters, or that's 1 meter, because what it'll all do is presume that they're all the same value, or the same unit, sorry. You do need to keep that in mind, because what this stuff does is it doesn't care about what you're trying to do. It just cares about producing a result. The other thing is as well, what is a common one is undo. In APDL, there's very little tools for undo. All you've got is just doesn't work, and you've got to go through a long process to delete something that went wrong. In fact, most of the time, most people, if they get something wrong, they've got to start again. And it is as brutally simple as that. Now, again, the only reason why I'm taking you through this is because it is something that's used, and I think it's very useful for you guys to at least see what this tool is. If you choose to use this, then you're welcome to use this. For those of you who are very much UCLan homegrown, Josh, the technician, was my project student. Josh designed an APL, an application programming language, a GUI to interface with this, which he was looking at what would happen if dust got sprinkled onto carbon fibre. Now, to explain to you what he did is he used this procedure. He then used Monte Carlo theory to randomize where certain bubbles would appear. Now, his inefficiencies is his dust, if you will, he sprinkled over it by drawing the shape of a circle. This circle was randomly appeared throughout the structure. Now we're going to build a simplified version of what he did, but what it meant you could do is you could put in the quantity of carbon fibre that was covered in dust, and then you could look at the shearing to see if it had any big problems. And some of the work he produced for his masters, some of the work he produced was incredibly impressive, because you were able to actually run some of these stuff and actually look at the shearing effect, at the effect of what it would do. Right. So now typically we've used static structural. We're not using static structural as of yet. I do want to take my time through this, and I want to go dead steady as to why I'm actually doing this. I will try my best to keep time very short as possible. If not, I am extremely sorry about that. But it is very important to me that we get this right. So now let me just scroll that back up, hide that. That's what we've typically been used to. Now the analysis systems, if I go to components, this is the bit I've never tried in Horizon. So this is either going to work really well or we're not going to be able to use it. So I'm going to left click, drag and drop mechanical APDL. Drag and drop it in, and so far so good. So what I'll do is just call this carbon sample. If anybody's had any problems with APDL as a tool to drag in like that, please do send me a message in the chat just so I'm aware of that that's happened. Again, where this is found is under component systems. So this is at the raw data side of how Ansys does its magic. Please, when you open this, don't be too disheartened because it does not look very pretty. So I'm going to right click on analysis, and here we go. Open in mechanical APDL. And now what it does is it goes to its subsystem sets. This writes into DOS, and amazingly it works. You've no idea how pleased I am. So let me just expand that. And this is it. For those of you who are a little bit older and like a little bit my age, you'll have seen something like this before. This was heavily used before. The most place I'd seen this particular thing used in the 90s and the 80s was one at Leyland Trucks and the other at BA. I'd seen this used quite a few places. I think more of a sister company, so MBDA, places like that, I'd seen this being used. So what we're going to do is take a bit of an intro to it. And again, I'm showing you this because amazingly, this will run on your mobile phone. This does not need stupid high computing power. It only needs stupid high price to actually buy the license. But as a tool, this will run on your mobile phone. And this is where Ansys really boast themselves out because they can do that. So what we want to do is, in the past, what we've done is we've clicked on automatic meshing. In this session, we're going to build the mesh. We're going to look at the libraries that's there for us, and we're going to select a library on it. Now, think of the node methods that we've used. We've used tetrahedral methods, we've used quad methods, and with you, we can actually decide how these nodes are going to talk to each other when we run these. So the automatic methods that are in Workbench, we're doing away with here. We can control this from the ground up. So this is my operational space. One thing to keep in mind, when I hit save here, it will save to wherever I'm actually loaded to at the moment. So if anybody's unsure, you can use a directory. And a directory is just basically what folder you're going to save to. Right, so what I'm going to do is first go to preprocessor, sorry. Now within my preprocessor, this is a lot different to what we've done. But again, I am stressing this is still heavily used, as much as it might come across as being a little bit unbelievable. So within here, what I need to do first is start to think about the type of mesh that I want to use. Now I can refer to mesh now because you guys have got a good feel for what mesh is and how this mesh is behaving and why we're doing what we're doing. So in essence, first I'm going to say to the system what type I want. So I'm going to go to preprocessor, element type, and then from there I'm going to go to add, edit, delete. And this is the first phase of what I'm going to do. I'm going to add a new node system. This is similar. Well, this is really, I should say, this is really what's going on in the background when you open up Ansys. It brings you these types of mesh methods. Now this is every single type of mesh method it can actually offer, and it's through the roof. It's very impressive. What we're looking at here is we're looking at carbon fiber, aluminium plating, carbon fiber. So what I'm going to do with that is I'm going to use a shell. The reason we do that is because we're now outside of the orthotropic behavior. We're going to be looking at isotropic behavior. So again, two components are the same and one is not. However, in our aluminium, we are going to say it's got that normal orthotropic behavior. I always get the two mixed up. Orthotropic behavior. Now, under shelling, I've got 3D 4 node. Now, really, what it's written, the code, by the way, is how many iterative times it's gone through. How many times people have refined it and refined it and refined it. But we're going with the 4 node 181. three-dimensional, and basically it is that quad method that we were using on the pipe. We can use a more refined method with 8 node, but for what we want and the sample that we're going to make, it's going to be rectangular structured by layers. So I'm just going to stay with my 4 node 181 method. Right, so now if I go OK, there we go. So now what it does is brings it in. It now loads that. We have that as a tool, but we've still got to edit stuff. Those of you who are going to get annoyed with this, massive apologies. It is it's very bit long in the tooth for setting these things up, but my God, when you're looking for solutions, this thing is quick. So I'm going to go options, and within my options now, I've got so many different things I can do. I can look at the element stiffness, and under that, I'm going to be looking at bending and the membrane. So I'm going to be, I'm basically saying to the system, my real focus is going to be around the bending and the membrane, and the integration option, reduced integration. Now basically what we know with the nodes when they're moving, if the nodes overlap each other, if 2 nodes collide, we've then got a cancellation of a matrices. We cancel one out, and then we can basically make 2 into 1 by cancelling out. Simple as that, because of the stiffness matrices. So we're going to be using that method on the reduction integration. Curved shell formation standard. This is just if we have a fillet, will it attempt to try and refine around that curve, and that's exactly what we're after. This is where I'm most interested. Storage of layer data. This can be just at one particular layer, so we can focus on one layer, or I can say all layers plus a heightened focus on the middle, or I can say just give me all the layers, and I am just interested in all the layers, so I can actually see what the whole thing is doing in one single hit. So I click OK on that. Now that is my mesh refined, that is my mesh setup, and I am now ready to start moving towards my material model. The numbers I'm about to put in, this is a made up carbon, and it was just because at the time I could not find a nice carbon, so I thought, right, I'll make a carbon up, and then I got a really good carbon, and then I had a student in this class who was doing the examination of carbon fibre for his project, and I didn't realise I was giving him the data to do his project. I had a serious roasting off a colleague. I had no idea. So I have made these values up. So if you sit there and go, well, that's well out, it is out because I've made it out. But what we're interested in is that failure region of the carbon itself. So I'm going to hit close on that. Now from there, what we can do is we've got our element type, we've got the meshing setup, but this is the meshing process setup. We've not meshed anything yet. Hell, we've not even got any geometry yet. So what I'm going to do is go modeling. Wait a minute, no, I'm going materials properties. Sorry, I'm not going modeling, I'm going material properties. And I'm looking to do material models. That's why I went to modeling. So I'm looking to go to material models. So we need 2 materials basically. We need one which is orthotropic, and we need one which is isotropic. And our first orthotropic material, which is our carbon fibre, again, kept getting it mixed up, it's orthotropic and isotropic, so we want this first material which is orthotropic, and this will be our carbon. Whatever you do, do not rename this. When we start to move on a little bit more, you're going to see why. Renaming it can be a huge pain in the backside. So if I go material model, I'm going to go to structural, and I'm going to go to linear. I'm going to put into elastic. I'm going to go to orthotropic. Now you see, I know this looks very clumsy and very basic, let's say. Now what I want to do here is I now need to know what my elastic modulus will be in my X component, my elastic modulus will be in my Y component, and my Z. So I'm going to use a modulus of, let me get this right, it's, I wrote this value down, so I'm just looking. Eight, 5, 0, 0, 0, 0, 0. And this is, this is, as I said, a very much made up value. So if you want to know how big that would be as a value to put in, that would be 8,500,000. So I'm going to copy that process again, 85. And then here we're going to finish on 10. Again, just making it up for the same. And this is now our representative of our carbon, or it has to be carbon, could be Kevlar, could be whatever fibre reinforcement that you're looking for. If anybody's curious, this is assuming perfect relation across that infusion. So no dry bits. This is the reason why the technician who was doing his masters, this is the reason why he did what he did. He was looking at, if you can't have that badness, how can you introduce it? Because it is a vital piece of what this is all about. So now we need a Poisson's ratio. Now for our Poisson's ratio in this case, we're going to assume the same all the way through. So I'm going to go 0.06, 0.06, and 0.06. Now we need the galvanized XY ratio. So in this case now it becomes 0.29. 0.29. Again, if you're wondering where these values are coming from, please do check the notes. I've got them on one that I've just called Carbon Fibre APDL. I've freed them up on Blackboard. They are there if you want to see them. If you are following me, I'll just hold up for a second just so you can see what values I've chosen for this particular material. Now the thing is with the way that we're assigning here, we do need to assign a density to this. It does need to know the density of the actual material itself. Oh. What I'll do now is I'm going to move to an OK. So now it's set up the orthotropic behavior of our target material, I should call it. But in this case, it's my pretend carbon. But what it does need is it needs a density defining. Now you'll notice with APDL, I am having to manually build materials in. This is a common thing in APDL where you've got to gradually build stuff in. It's one of them aspects. Just to show you what I did in density, I've added a density of 2,200, and then I clicked on OK, and what it's done is it's added me a density into that material. So there. Then we've got the material values there. Making an edit to a material when you come back, I would always recommend that you have to delete that material and then make a new material again. This system does not like you going backwards. It's been the biggest criticism for years, and this is one of the reasons why they introduced Workbench, because Workbench essentially bolted to the front of this and it did all these little bits in the background for you. Made life so much easier, so much easier. In many ways you just felt a bit spoiled because it was like, yeah, it's doing it all for me, which is great. Now what I'm going to do is I need to add my aluminium to this. Oh, sorry. So I'm going to go materials, and in my materials now I'm going to add a new material. You see, defined by ID 2. And this system actually doesn't like you putting specific names into it. It prefers to operate in integers, not floating values. So don't go 0.0021 for an identifier. Must remain as an integer. I would always recommend that. So now we move forward from there. We can now move towards a difference in material, and we need an isotropic material. This is going to be our aluminium state. With the aluminium, again, we'll see Young's modulus. In this case, obviously, it's one value that I'm adding for my aluminium because it's of its orthotropic behavior, isotropic behavior. So I keep getting the two mixed up. Yes, so isotropic behavior. And with this, I'm just going to add 6.9 to the power of 10 for my aluminium. And then for my Young's for my Poisson's ratio, I'm going to use 0.31. And then OK. Now with that, now we don't need a density for this case. This density will be fine. Oh, apologies. Yeah, we do. What am I talking about? So we've now added this here. We do need a density. What we're talking about, we need to add in the density of our target aluminium, which is going to be 2700. Again, I've just pulled these values straight. Well, for aluminium, I pulled these straight from MatWeb. And so now I've got my carbon, which is now my target number 1. And now I've got my aluminium, which is my target number 2. So now I've actually got everything set up exactly as I want it to be. I can now start to look at the structure. Now this is odd. A lot of people don't like to do it this way. A lot of people don't like to set up carbon examples, or I should say a composite layup example. They don't like to set them up this way. They prefer to have the geometry first and then operate from there. For me, I like to lay it up, and because I share my office with Tony Broad, who's, for those of you who don't know him, he's a composites king. He really is. It's always been interesting trying to learn from Tony about the best laying up procedures and things like that. So the important things about laying up, the orientation of the carbon, how it's been set up, where it's actually sitting, how the interface is there. That's why I focus on that first. Introduce the geometry, and then it will just be what I tell it to be. So I'll close that, because that now is my materials model set up. Again, it's very anticlimactic, because you come to the end of this and go, yep, still not really seeing exactly what I'm going to be laying up with this. So from the process now, I'm going to go to sections. Now with sections, I can now isolate down a little bit. 2 seconds. I think I have a question. Do you have a question? Has it returned? My sound? Ah, right, okay. I just wanted to pause because if something went wrong with everything, it's just nice to check. I'll just before I continue, I'll just double check that I've got sound active. Yeah, I've got my microphone active, so it should be capturing. If anything's gone wrong with this, I will have to just record it, because this is quite useful for I think everyone. There is a lot of uses in this. Anyway, so I'm back to sections, and on here now I've got all different types. Now you'll recognize that was beam. So in beam, that is what we did the other week with linker elements. So, but what I'm going to do is use a shell. And here, if I go to layup, I can plot sections, or I can add edit. Now, before I move on to anything, I've decided I'm using 3 sections. I'm going to use one carbon at 1mm and the other at 20mm. Carbon will be at 1mm, and my alley will be at 20mm, and then my other carbon section will be at 1mm. So I know I'm going to use 3 sections for this. So I'm going to go add for my 3rd layer, and I mean for my second layer, then add for my third layer. Now I'm in control of what I can do. Now, just so, I've just realised I've not actually explained. Have you not noticed I'm not operating in any units? Nothing is said, meters, millimeters, pascals, whatever. This is where, if I'd have made a single mistake, I'd have to start again. Because you kind of go, oh no, I'm actually operating in meters. So I'm going to go, for my first layer, I'm going to go 0.0001. And you see there I've got material by ID. I'm setting that to 1. So that links the two relationships together. Now orientations, this is as literally as it sounds. If this is presuming that the x coordinate is your beginning orientation, so if you imagine that's your layup and they're all on the top of each other and they're all in line, if I set that to 90, you see there, it gives me that little drawing, and it's just to give you an idea of where these layers are sitting when it actually operates. Moving to the next phase with this, I'm going to set 0.0. Oh, that nearly went wrong. 0.02. Oh, I set that too small. That looks quite small, doesn't it? I think I've set too many. Set that way too small there. Right, yeah, I set that way too small. It's a lot smaller than I wanted it to be. And what I'm going to do on the third layer is I'm going to set this 0.001, which is the same process again. However, at the moment, you can see there, I'm still operating. Everything is in my. It's not really carbon, I'm just going to call it my composite material. So my composite material is my value for 1, but if I set that to value for 2, it now gives me a bit of a change colour. It's not the most sophisticated materials in the world, it is the way that it is. Now, somebody said to me recently, when it presents the geometry, how does it know where in the actual process to make it from? So what I mean is, for those of you who are CAD savvy, you'll know this as offsetting or extrusion. When it's to extrude the actual process, which way does it go and how does it do it? So if you look here, we have mid plane, bottom plane, user in input location. You can actually define. I always leave it as mid plane in this case. So it in anybody's perspective, you can think if it's 10 millimeters, it will be 5 plus or minus to give you that type of an offset. So that's how this one is laid at the moment. You can change that. More than happy for you to change that. When we move forwards, though, you're going to start to see a little bit more as to why certain things have to be done a certain way. But this now is our orientation. If you wanted to add more layers. Now, the Tony I share my office with, and I'm sure some of you as well who've been on placement at places like McLaren or at any of the race automotive areas, you'll be able to tell me better about the layout procedures. You can often go 45, 90, 45, then 0, and it's about the reinforcement of that layout. But what I'm just trying to show here is how you can control that orientation. So if you wanted to build a lot more in depth in there, you could do that. If you know the relationship between carbon and Kevlar, there's no reason why you couldn't have a carbon material, a Kevlar material with a sandwich in the middle, and then repeat the same process on the other side. There's so much you can do with this. And this is why a lot of researchers use it, because you can start to code, you can actually code some of these operations. And it allows you to manipulate what the geometry is doing, so you can get an even more accurate representation. This is also another way that you could look at the relationship of polymers when they're interfacing through fuse deposition. Anything like that, that's what this will do. Right, so I'm going to click OK. And now we have the meshing set up. We have the procedural process set up, because when we did all layers. Then what we've done is we've set up a layup procedure through our shells. So it now knows that whatever geometry I put onto it is going to be assigned with these meshing procedures that we've already defined. So it puts us in a good position. If you've not done already, do save this. So I'm going to save that. Just because if anything goes wrong, you'll come away and go, oh hell, lost it. So do make sure you save it. Again, you might not want to use this ever again, but I do think it's incredibly healthy for you to see it. Right, so I'm going to shrink that down, and then from there I'm going to go to my modeling. On my modeling now, again, if anybody is CAD savvy here, this is going to make your skin crawl, the process of making it. For those of you who've done AutoCAD before, you'll be well at home. What I've gone is to modeling, I'm going to go to create, and I'm going to create myself an area. Now this is, for those who have done my CAD classes or those who do this in their workplace, we're going to produce what will be a surface model. Well, this is the painful process of making it on here. So we move from areas to rectangle, and then all I'm going to do is go by dimension. We're going to make it 40 mil, but I'm going to use the origin as my base coordinate. So anybody who's doing my advanced CAD, by the way, you'll know coordinate base with your two base outputs. So you're drawing a line. We are drawing a line, but we're drawing a corner rectangle in this case. But in Ansys, what it asks you to do is give a key position of each point of this coordinate. So back left, front right, well, upper right I should say, lower back left, and upper and lower front right. I'll just pause for a second for anybody who's following me on that. I do want you to see that, that's all. When we do move into the workbench and we go through workbench as an example, you can have such a different perspective. You go, oh my god, why did we not do this from the start? It's just because, again, this is still heavily used, regardless of how much this may irritate people. It genuinely is still used quite a bit. And again, I still maintain that you guys, it's very important for you guys to see it. So I'm going to click OK. What we end up with is that. This is, now for anybody who's unsure of exactly what the hell you're looking at, this is just your rectangular structure. This is the top profile of what your carbon fiber sample is going to be. We just laid out them dimensions onto it. And what this will do is this will push downwards and we'll be able to create a visual representation. Now when these are called shells, so I'm going to see if I can just spin this round, if it'll let me. You can let me spin you round? Nope. Brilliant. There we go. So you see up here, I've just gone to my isometric view, just so you can see what we're seeing. So for anybody who doesn't know, a surface is not volumetric represented. A surface is the surface area of a key thing that we're doing. In this case, this is our sandwich component. 2 seconds. Good question. So I'm just going to pan this back to... I'll answer that. So one of the groups just asked, is it possible to load the surface model as an IGES? Very true. It is possible to do that. You can import it directly in. However, it does become problematic. The system does read it. It can lead to some levels of crashing. However, bear with me, because when we shift over to Workbench, we're going to be able to complete this far quicker. But the reason is with this, you tend to try and build your samples in here. You never have detailed geometry in here. You tend to have small sectional pieces, pipe sections, sandwich configurations, things like that. This allows you to just look at the layout and the procedure that you're using, and then you can look at what this material will do under certain conditions. However, if you wanted to move towards assemblies, this is where you start to move away from using APDL and use Workbench. Hence why we're going to move in this a key direction. Right. Sorry, I'm starting to just hear my own voice, if you know what I mean. Right, so what I'm going to do now is we've got this set up. Let's get seeing some. I know it sounds silly, but let's get seeing some action as to what we need to be doing. Now, modeling's complete. I've done my sections, material properties set. I've got my element types in there. Let's get into meshing. So from my meshing, there's all different types of methods for meshing here. We're not going to waste too much more time on that. We're going to go to his meshing tool. And in this meshing tool, again, looks really, really primitive. But what I'm going to do is I'm going to use a smart size tool. Now what I can do is I can use the automatic, and with the automatic it will probably just break it down into large base quads. So we'll end up with huge triangles on it. Now I'm going to make this semi-fine. So I've clicked onto smart size. I've dropped it down to 4. The 4 in this case is going to be quite refined. You'll notice down here we get to mesh, we've got free type, so we're prioritizing with a quad approach, but our free means that if it hits any key difficulties, what it will try and do is bring in tetrahedrons to try and solve any burning problems. But it's basically, it's a square, so we're never really going to hit major issues with that. So I'm going to go to mesh. Now, when it comes into here, if you had lots of key areas where you wanted to define, you could click onto it and choose it. Or you can just click pick all. And what it will do is just choose the whole geometry and mesh it. Anybody struggle to get that? If you did struggle, apologies. It can be a little bit temperamental. I am, as ever, going to upload this model in a zipped file so you guys can actually look at it and go, oh yeah, that's what it's doing. Trouble is with this, it's hard to see the settings. When you go back to the old stuff and you look and you go, it doesn't tell me anything. It's a little bit frustrating. But what I'll do is I'm going to close that now. My meshing's done. I am happy. Right, now, you kind of go, that's great. But that really does not look like the carbon fibre sandwich system that we're looking at. Now, because we've got this behaviour of orthotropic and isotropic interacting with each other, what we now need to do is we now need to introduce, we now need to let Ansys mesh it for us and tell us what this would look like as a mesh. Because we don't really have the geometry. So what I do from here is go to plot controls. Within my plot controls now, I can assign all sorts to it. Apologies. I'm going to go to style. Now, in my style, I've got all different types of things I can do. I can make my nodes look a different color. I can do all different types of things. I'm not really fussed with that, if I'm honest. But what I am interested in is size and shape. Now, what Ansys by default tries to do is save your computation. This isn't much. I mean, this is when computation was really struggling for something like this. But it still does it. And this is why people praise it, because it does away with all the BS that you don't need to see. However, it also does away with things that you do need to see. So display of elements is turned off. If I click on and then click OK, now what we've got is something else completely. Let me see if I've got my orientator. Where's my orientator on here? I think if I press Control, yeah, I'm going to press Control, middle mouse button, and that will allow me to spin it. Now I'm just trying to get into a nice orientation now. And let's have a look. So if I rotate in Z, oh, not in that one. Yeah, it's a bit brutal for being able to move around this system, but that is our carbon fibre layout. That is the aluminium plate in the middle, we've got a sheet at the top, and we have a sheet at the bottom. One side of it is 90 degrees, the other side of it is not, as we know, because we've defined it to be that way. Now, what I would like to do is just set up. What I would like to do is start to set up the next process now. We've now got this geometry, we've got us meshing in there. Let's start to set up about what we're going to solve for. So within the main menu, I'm going to go down to solution. Within my solution, it needs to know a few things. It wants to know exactly how I'm going to set things up. It wants to know exactly what type of analysis type I'm going to do. So I'm going to go to analysis type, if it's going to let me. And someone's beeping me like mad. Go to new analysis. Within my new analysis, this is what the type of simulations it can run. So with my analysis, I'm going to go static. Click OK. And now we're into our first simulation time. Now, you are going to, if you are following me with this, I'm going to go dead steady with this because this can be so annoying. What we're looking at here is the mesh. We can only define on the geometry that we've got. In this case, is a surface. The extrusion of that surface is what allows us to choose where we're going. So what I mean is, I will show you now. So what we're going to do is we're going to define a force perhaps around here. We're going to apply a force to it, and we're going to look at what this geometry does and look at where shearing could occur when it happens. Because obviously with carbon fibre, it's like a ream of paper all stacked up. If you bend that ream of paper, what it essentially does is they slide across each other. And with carbon, when it's laid over the top, the first thing that carbon always tries to do is shear itself apart. It attempts, from the first go, it attempts to delaminate. What we want to do is, can we see that happening between the aluminium and the carbon, or I should say composite material. Right, so I'm going to go to solution, and from here I'm going to define loads. I'm going to go to apply, I'm going to go structural, I'm going to go displacement, and now I'm going to go on lines. The reason I'm going to do it is because I'm going to pick two lines. So when I pick it, that's all it does. And you see here, I've got an arrow. Now, if I was going to pick here, for example, I left click, and then that picks it. However, let's say I didn't want to pick that, and that was the wrong line. It is the wrong line, but what I'm going to do is right click once. You see the arrow pushes down. That response of it going down is in cancel mode. So if I click it now, turns it off. So I've got to right click again to get the arrow pushing back up, and now I can click here and click over here. And this is because the nodes that are on here don't class. They're not classed as geometric lines. What it's actually doing is it's picking on the surface that we modelled. And if you've got both then dotted lines there to mark that it's actually been picked, click OK, and what you should get is your fixture marks. Oh, that went wrong. Where did that go? Oh, there it is. Right. Apologies. No, you won't, because we've not designed it. We've not said how much it's going to move. With displacement, we can displace it in a key area if we wish. We can rotate it around a key axis if we wish. With this, I want it to be fixed. So I'm going all degrees of freedom. Value for displacement in this case is going to be 0. And then now if I click OK, we get our markers here, 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 and here to tell us it's now fixed. Oh, and then finally, we want to be able to put some force onto it. We want to be able to apply it with a bit of a hit, and we're going to go with, I've got 2,500 newtons. And what I'm going to do is I'm going to go to my force. Oh, excuse me. I'm going to go to apply. displacement. Oh, sorry, structural force. This time I'm not going onto lines, I'm going onto nodes. And this is where you can pick. So don't forget, with the arrow pointing up, I'm in select mode. With the arrow pointing down, I'm in deselect mode. So what I'm going to do is I'm going to pick a node here, and I'm going to pick another one here. These two nodes are going to be my target now for what I'm going to hit, or where the force is going to be applied. I can put this in the middle if I wanted, but this point really tells us any type of shearing that's occurring at each XY, YZ planes. So if I click OK, comes in now and says what is the direction of force or moment that you want to apply. For me, I'm going to go FZ because I'm going to act down onto it. And then from there, I'm going to go minus 2500, so 2500, and then OK. If you've done this right, we'll get a red arrow that appears where you just clicked. These red arrows just confirm it is very old school. So in Workbench, we've had this nice big sexy red arrow that tells us which way it's going. In APDL, we get a stick drawing, but again, it is using very little computing power to actually get this geometry built. So this is again where this is heavily praised. Now this is amazing for solving. I'm going to hit save because again, don't forget this is still software, and if it dies, this especially just stops working, and you go brilliant. So if we hit save, we can always come back to it. This is one thing it's always been good at. It doesn't really corrupt a lot of its solutions. Once you get it solved, it is solved. But if it crashes halfway through a build, you do lose everything. So I'm going to go to solve. Within my solve, I'm going to be looking to solve my current situation. This now comes up and tells me at the beginning of the status, do I want to do the current? I do want to run the current. Click OK. Give it a couple of seconds, and that's it, done. And again, your geometry, in this case, this is just simple geometry. My student who was running these interestingly run 4,000 variations of this in 20 minutes because he coded up it just running through. But it's because of its ability to just not suck up every single piece of memory it can find. It's crazy quick and crazy powerful. So once you've got the solution complete, let's take a look at what we're actually getting. So I'm going to come back up to here, and what I now want to do is go to General Post-Processing, and now what I want to do is go to Plot Results. From there, I'm going to go to Contour Plot, Nodal Solution, and this is what it can give us based on the results it's been getting. So first things first, let's take a look at degree of freedom. I'm going to do displacement vector sum. So this is every piece that goes through. This is in Workbench when you get total deformation, or total displacement. That's what this is talking about. So I'll do displacement vector sum, and then click OK. My nodes have shifted. Damn it! It's just because of this bloody. Anyway, yeah, this has happened because when I'm clicking on the screen, it's clicked. Yeah, anyway, it's clicked on the screen and it's put them in the middle. However, we are getting the result. Thank God. Under that's telling us that we're looking at to the -4. So what's that? If we're in meters, 3. So it's still moving a little bit, isn't it? Only a little bit though. And that's plus or minus for each direction. So yeah, it's moving a little bit. But what I'm really interested in now is any types of shearing that's occurred on it. We should be able to pick that up by looking at our nodal sum again, but looking at shear stresses that are occurring around it. So what I'm going to look at is my XY shear. Let's have a look at ZY shear. So this is shear that's acting around this side. I mean, it's not going to be much, but it's nice to just see it as an overall. So if I bring that back, and I'm going to go to stresses, and scroll this down. There we go. So I was going to look at YZ shear. Click OK. Yeah, as I can imagine, there's not much there. It's not a big surprise, but it's just nice to actually take a look. Obviously, the big action in this case is going to be appearing more in my YZ, because obviously the force pushes down, and the reaction of the shearing is the relationship of my carbon to my aluminium plate. So if I click OK on there, we should get these. Now you can see here, based on the aluminium itself, the aluminium does record shearing around these key edges. On the size of it, even though technically it's probably not sheared itself away, these are points where shearing could occur. So it hits down, and as the force is hitting down, the behavior is coming at these tips, which you would imagine, because it's hitting down, and then it's like I said before, if you have a ream of paper, if you're hitting down it, the top edges will be the first points of protocol where that shearing is occurring. So around these key particular areas. Now, can I actually rotate this bloody thing round? Oh no, I don't want that. Bloody shortcuts. Let's try that. Is that it? I often wonder what this bloody software is doing. Right, so you can see there that the highest points actually come here. Can I zoom that out slightly? Yeah, see that the highest points of shearing occurs here, and this is just because my points were impacted. You can see here I'm furthest to the left, but when I'm furthest to the left, the highest record actually comes at that point over here. And again, in this example, it is assumed to be perfect relationship of the layups between them. If you know your materials, if you know your material data to actually add this into it, you can start to build true representations. If you know the relationship of something like a honeycomb structure, so a honeycomb aluminium structure, you can implement that into the relationship as well. So what you could have is, I don't know, 5 layers above, honeycomb core, 5 layers beneath, and then start to simulate that. And that's when that big question started to come out of Josh when he was a student. He was really looking at, that's great and this is perfect, fantastic, but what is the error? And he found the error to be quite interesting. Depending on how it was done, he found the error to be very little between the simulated version and the physical test. However, if there was any inconsistency, if it couldn't be replicated all the way through, and there was any slight changes, it would lead to mass levels of errors. So he was trying to recreate them errors in his work, and very impressive. But because of APDL's ability to be able to do what it can do, it made it easier for him to be able to do that. Right, I don't know if you have done, please do hit save. What I'm going to do now is I'm going to exit from APDL. I will be uploading this model, so please don't panic too much. I will be uploading this model. As promised, I'm going to show you the alternate way of doing this. Save geometry and loads. Okay. So it comes back out, and that's all I've got sitting here. Is that going to let me pass anything on? Yeah, I mean, I can take that data, but I don't want to. What I want to do is build in to a different example. What I really want to do here is actually build in a bit more of a more trickier example, which on APDL would have taken us an awful lot longer. What I would like to do is lay up what would be 5 layers of carbon for one surface, and then perhaps 3 layers of carbon for another. quickest way for me to do this is I'm just going to open up SolidWorks. For this geometry, by the way, anything that I make, I'll upload it. It's not going to be a complicated geometry. I'm literally just going to make what I've nicknamed before the U bracket. Unless I may actually have it already on Blackboard, which probably going to make life a bit easier. 2 seconds, let me just check. I do. Right, so I've just made it available. So this geometry that's on there is called carbon sample. It's just a big old U bracket. That's all it actually is. But what I'll do here is just recreate something like it anyhow. This example here is because I'm aware of anybody who is perhaps doing carbon fibre for a project or carbon fibre for an assignment or anything like that. I'm aware that there'll be some who are interested in what if you don't have equal layers that move across key particular areas. What I'll do though for a start is because I'm waiting for SolidWorks to load up for me to actually take a look at, what I'm going to do first is drag and drop a static structural. I'm keeping these on the same save, but I'm not relating these two together because I'm going to have these slightly different. So we're going to be looking at the composite, my engineering data. Now in my engineering data has all the models of the materials I'm using now. So I right click and then go edit, models that I'm using now. That is all. And what I'm going to do is I want to add in carbon. Now I'm going to pick a carbon. I should point out, these carbon models are not accurate. I did have one student one year who's decided to perhaps take a look to see how accurate these models were, and he didn't find much luck at all, so he had to build his own models. But the beauty is, on what we're going to look at really does explain why and how you've got to build up models to be representative in your carbon, in your SolidWorks stuff. Right, so what I'm going to do then is I'm going to go to my composite materials. Within my composite materials, you'll see here I've got woven or I've got unidirectional. I'll stay with woven, do a pre-preg. We can do wet pre-preg of different areas, but again, we didn't have much luck on what these were. So let me just drop that. So please don't copy too much on that. But again, what this does do is it really does show you how the tensile behaviours, compressive behaviours, your shear behaviours are actually set up. Or even when you come to your elasticities and how these are set up, or even when you come to your, it shows you how carbon needs to be set up, which is great. But what I want to do is I'm going to assign a woven pre-preg 230 gigapascal epoxy. By clicking on the tab, I've added this into my library, and beneath here you can see here we've got some resin epoxy, or you've got honeycomb. Now, if anybody's unsure, if you look at the actual honeycomb layout, this is an aluminium honeycomb layout. It's aluminium honeycomb structure. Now, if you chase that link back, you can actually find where that came from. For argument's sake, let's bring in an aluminium honeycomb, and then let's go back to the engineering data. You see now we've got our two target materials. Close that down to here, and from my SolidWorks. I'm just going to quickly make a piece of geometry. Again, the geometry in this is not the most important thing. What's the most important thing is that you actually see about how to lay up different faces to be representative of what you're wanting to do. So I'm not going to make a super sophisticated piece of geometry. All I'm actually doing is just making something for me to build on. So I'm going to sketch onto there. I'm going to, I'll just make an L bracket actually. Make an L bracket, but I'll make these in different relationships. And that's it. That's all I'm going to do. And for this, I need to do a surface extrusion. Don't forget I'm operating in shells. In CAD, these are known as surfaces. So my extrusion is irrelevant in this case. I just want this to be just something that I can operate on. So I'm going to save as. I'll just put this in. I'll put it there. So I'll call this carbon sample. Carbon sample. Let that load, and then I'm just going to close that. I don't need that anymore. So I'll right click. Same method of import that we've done before. So go import geometry. Going to go browse. And I'm going to jump back up, and on here I should be able to find not much actually. There it is, carbon sample there. So I'm going to carbon sample, click open, and as I said last week, when it comes in it's saying review me, make sure I'm usable. So I'm going to right click in, going to quickly go on to edit. I know we're running close to time. This process now is far from what we've just done in APDL, but you'll see that variation between it, and it will lead to further questions. I know it will. I know it will. So click on to generate, exactly like I did. However, what's great, that worked out well. I'm going to reload SolidWorks. Oh, that caught me off. That's a swine. Right, 2 seconds. I've got to just open SolidWorks back up. Should have left it open. Let me come back. I hope I can get to the end of this one. This is so good. Okay, it's freezing me over. Don't worry, I'm actually going to back up. Just because you can never trust exactly what you're getting. I do have a backup. It's still a little bit frozen up. Is it still frozen up? It has frozen up. Right. As I said, I do have a backup on this, so I'm not too fussed. Right. So what I'll quickly do is I'm going to make that geometry. So under my geometry now, I'm just going to make a fresh piece of geometry. I'm going to have to make it. I was running on Horizon, but because I've been going backwards and forwards, I think I've frozen it up. But I do want to get to the big finding on this. So I've come into here, and all I did again is I just drew a piece of geometry up here to here, and then over to here. And then all I've done is gone surface and extrude. And it's just to give me a bit of distance across it, so I'm just doing a bit of distance across, and then we went OK. And that is the piece of geometry, and all I'll do now is go save as, and I needed to export this. That was my biggest problem. That was where it didn't work out too well, really, because I needed to export it in a better geometry. Now I always use step 214. You can use IGES formats, you can use other formats. I just had the most luck with step. That's all that is. Yeah, it's locked me up as that one. So you can always use step. It doesn't matter. But what I'll do now is I'm going to just bring this back in. So I'm going to bring in my engineering data, and under my engineering data, I just need to bring these materials back in, just because I'm running on my backup, just in case something went wrong. And again, I used 230 wet, 230 pre-preg, and this was woven. And I also brought in an epoxy, not epoxy, I used a honeycomb structure. Went back to engineering data, and there's my system. So get rid of that. And now all I'm going to do is import my geometry from wherever I put it. I think I put it on the desktop. Did on the desktop. Import in, and then all I do now, like before, just go on to the actual modeler. Allow me to assess or review that modeler. In a minute now. So it brings it in, and again I am just catching back up where I just was. Now when this comes in, click on to generate. It reads the open file, and that's what it brings in. One thing I do want to quickly show you is, you see on the bottom left here, if I expand that body, you see there it's coming and it's actually down as being a surface. This is purely because it has a thickness of 0. This kind of replicates that process that we just did on APDL, where we were gradually building that piece in, as this is a slight change to that. So I'm going to close that. That's all I need for geometry. That's all I literally need. And again, this example is just to really tie in the reason and the speed difference. Now you've got a workbench to operate with, but the one thing I do like about doing APDL is it kind of makes you sit back and go, wow, you know, all that stuff's going on in the background and I don't have to worry about it. So it really does give you a bit more appreciation as to how the nuts and bolts of these systems actually are functioning when it comes to that. So the processes that we were selecting, it's just not been my day with that. Okay, let me just jump back. So-called backup, that went well. Right, okay, let me come back. See if this will let me do it. Just been so unlucky with this morning. This is just opening up my original copy. And then after this, I just uninstall everything and delete it. I'm kidding. Never do that. So this is the original one that I did. And what I did wrong is I didn't save it as a step file. So bring that out. And I'm just going to export it as a step file and put it in the same spot. Click there, and I should be able to go back to Ansys now. And if it's now, there we go. Right, bring that back, and if I right click, God, if I right click and it works, I'll be so happy. So on to step. Again, I'm just using that step file again. And we're into geometry, and I go back to it. Really what I'm after doing is getting it attached. And my backup failed. I'm not sure why that failed. That's the first time it's really happened to me, but It's the first time for everything, so I click on to generate. Part's in there, it's brought in, it's a single surface, as we well know, so I close that surface off and then go on to setup. Then I'm going to right click and then go to edit. Amazingly, we are going to get to the solution, thank goodness. So it's now just importing. Let's get rid of all these because these are all just there we go. Right. He's getting there. Right, so when it comes in, what we'll do is we'll apply the similar type of scenario here. We'll fix it on this face here, and let's pull it apart and let's see what happens when we pull it apart using the 2500 newtons just on this simple layup. But what we'll do is we'll do 2 layers of carbon. We'll orientate them at 45 degrees apiece, and then we'll do a sandwich in the middle. Then we'll do 1 layer of carbon to sandwich to 1 layer of carbon. Then we've got a comparative between the two. And what we'll do first is come on to geometry. You see here it's coming with a question mark. This is because it's saying whatever you're doing, there's no thickness to this. Sort it out. So what I'm going to do is first just assign a relationship of carbon fibre to that. Just for the minute. You'll see what I'm going to do soon. But I'm going to right click, insert, layered section. First layered section is coming from here. I'm going to apply it to there. So that's where the first face goes. Wants another coordinate system. I'm going to use the normal coordinate system. Which is the body-centered coordinate system. You can change that depending on the scenario that you're working on. If you look here, we've got offset, middle. I'll use the middle offset again, or we could do top, bottom, whatever. These may collide, so we might need to. So let's just get this one built, and I'll probably go, we think, if I go from top, just means I'm going to move outwards a little bit. And then if we go worksheet, now within my worksheet now, what I end up with is my layers. Now you've seen this before, it's what we've literally just done. Now we agreed 5 layups on here. So my top one is going to be my carbon, my next one is going to be my carbon, my middle one is going to be my honeycomb, my next one down is going to be my carbon, my next one down is going to be my carbon. Now I agreed a 45 degree orientation from X, so this is, we'll go 90. Let's go, oh sorry, that's thickness. We'll go 90. We'll go 45. Oops, 45. Then we'll go 45, and then we'll go 90. It's just me putting these together, and maybe we could have got even less actually thinking about it. And then what we'll do is assume the same thickness as before, so 0.001. And for my thickness of my honeycomb, I'm going to presume the same dimensions again. Right. So that's for that particular layer. And if we come back, it refers to here. So we need one for down here. So what I'm going to do is repeat the same process again. I'm going to go layered. I'm going to go layered, and I'm going to click apply onto there. I'm going to do offset, and then I'll do boundary again. I'll come from my top face, and again, I'm just going to repeat that process. Here though, there was only 3, if you remember. So add layer, and add layer. My top layer here becomes carbon, my middle layer here becomes honeycomb, my bottom layer here becomes carbon. I'm moving relatively quick there because this is crazy quick in comparison to what we've just had to go through when it comes to setting these up in FEDL. But this does remove that greatness that you can do if you wanted to look at inconsistencies in your carbon. Because in this case, you don't get that option. In this case, you just get, these are perfect, don't care. Now, what this essentially is saying here is it's saying, look, you've got this all here, but it needs a thickness just in case you've missed anywhere. So let's say you've got 20 different layers all over the place, and you say, look, everything else has got this thickness. So you put a default thickness in there. So on here, if I just said, look, everything else is 0.0001, it doesn't matter for this one, because everything has already been given its representation in the rest of the places. Expand onto here, we know we've got these structures in here. Let's quickly mesh it up. Let me just check on my carbon faces. Yep, they're all there. Okay. And then let's have a look at generate full mesh. Right. So what I'm now going to do is I'm going to fix the positions. Now I'm going to do fix support. From my selection tool up here, I'm just going to select edges. I'm just a little bit conscious of time now, so apologies if I speed it up a bit then. I'm just conscious of time. So I'm going to fix on that face, and then I'm going to come back across here. Let me just check. Have I selected? Yeah, it's all made. Environment. Yes, okay. To just double check. And then I'm going to add in another, I'll put in a force, we'll at minus 2500 newtons here and here, and it's in the Z component. I'm going to use components. I like to know which way it's going. So I'll go minus 2500, and then we can solve. If I've not missed anything. Hope I've not missed anything. Then onto here, I'm just going to look at my deformation. Trouble is, the geometry I've brought in is bloody huge, and that's what I've done with myself here. They both got the same applied to it, but what is interesting, oh, 1 second. What's interesting with this is the lower face was the same configuration. However, on the lower face, it was two layers of carbon and one central core of honeycomb honeycomb structure. And however, this up here was this was 1 to sandwich core to 1. This was 2 by 1 by 2. And you look at the actual displacement and deformation between the two. This has clearly gone to a much greater. So if I go right click and then I go on to stress and then I'll look at shear. If I do shear stress in this case, this is XY shearing. I think if one definite thing that's going to occur here will be in the XZ. So if I look at my XZ, we're probably going to highlight quite a bit of shearing there. Because obviously it's that process there. And that is just really coming from this process here, but you can see there that there is concentrations here. I mean, the issue is my mesh is still quite large. It could do with being refined. Of course it could. But again, I'm just conscious that we're going to run out of time. And if I then look again, and now let's take a look at the YZ. So in this case, it's maximum, well, we'll just go a maximum of 5,379 megapascal, which is quite big. Evaluate again. If you look there, now this is the plane which is referring to this shearing. Whoa. Shearing's always going to want to occur around it, but look at the difference between it. We're down almost 2,000 megapascals of shearing that's occurring, and that's purely from adding them extra pieces. Now the thing is we didn't change orientation. Is orientation in this case something to be considered? Of course it is. Of course it's something to be considered. But it does really start to present that if you're doing something like a tub, if you're doing a monocoque, if you're doing so many different applications of it, if you're doing a carbon fiber frame, if you're doing carbon fiber handlebars, if you're doing anything that relies on a composite layup, if you're doing body armor from say something like an American football player, if you're doing anything like that, you can actually build it and you can actually look at that layup and you can verify that. Now, those of you, again, I know I keep relaying to members of staff that some of you guys won't have met, but one of our members of staff, Tony Broad, he does a lot of carbon testing, and we can use the tools that we've got there, tie it into this to get a nice overlap between the two. I mean, I know what I've gone through today really does only even just about scratch the surface onto a huge area of research and development. But what I really wanted to present to you here is two different key ways of being able to have different layups on assemblies or bodywork, or if you want to just look at sample pieces and look at that, different ways of approach towards it and different ways of actually doing it. Outside of here, when it comes to verification of something like this, obviously with the sample piece in APDL, you'll be looking down the road of looking at laminate theory, where you're looking to see about them shearing aspects that occur across it. That in itself is a monstrous area, and it's a fascinating area. So if anybody is interested in some reading material, the recommended reading on this, there is one particular book which is Ansys driven, and it's a really heavy going academic book, but it is really good. Now I know I did promise everyone I would upload some books. I'm going to actually upload them to the files on Teams. I'll be doing that this week. Do take a look at them. These are to progress your knowledge further. There will be console books and there will be Ansys books. And a lot of the Ansys books are APDL driven, but they are just to really advance your understanding of what we're doing even more, just for you to develop your skill sets even more. I have lots of these books. It is a really, really interesting area. Right, we're on 10 to 1. Apologies for the freezing up on these softwares on here. It just, as ever, I'm impressed that I managed to get this thing to actually run in the end. This sample model that I put together, these two here, I will be uploading to Teams, so at least then people can download it, do what you want with it, do take a look at it. If there is any burning questions about it, do let me know. The assignments marks for now, I'll be getting them out this week, and then the next one I'm going to get it out as quickly as possible. You'll probably see it before I introduce it, and I'm doing that just because I want you to see it and be thinking about it. One area that I am going to be doing is I'm going to introduce an example of simulating a bow. I'm looking at different materials for use in bow, as in archery bow, and I'll be looking at a recurve bow, just because it's just something I've been going down the road in at the moment, actually building a bow from scratch, and it's a fascinating thing. So if any of you have done it before, yeah, any indicators will help. Right, so let me just stop recording on here unless there is any burning questions. Just stop recording.